Try to get through much as you can, free up tomorrow. All right, so what I want to look at today, we're going to look at two things. Well, actually three things. We're going to look at some attributes of functions. So we want to take a graph and we want to sort of remind ourselves about the vocabulary that we use to describe a graph and what that means in terms of the graph. So for example, we've got this function graph. If we want to talk about the places where the function is positive, or another way of saying that, where the function is positive value, I want you to try to give me an interval. And when I say give me an interval where the function is positive, am I talking about x values or y values when I'm asking for an interval? Well, kind of. I mean, I'm asking for x values, but the y values are important because the y values are necessary in determining where it's positive. But whenever we're asking for an interval where a function does something, it's implied that we're talking about a part of the domain. We want to know the x values where that's happening, okay? So we're looking, I want you to give me back, in a second, you're going to give me an interval of x values where the function is positive. But first, let's decide, how do we know where a function is positive? What does that look like on our graph? What does a function look like when it's positive? What about the function tells us it's positive? Well, okay, there's a dot there, true. Which one? Okay, the top one. So there's an example. Good. So now we're making some progress here. So here is an example. That is a correct example of a value where the function is positive. How come? What about that? What made you decide that's where the function is positive? So it's above something. Above what? Zero. Oh, yeah. By zero, you mean y equals 0, right? Which is what on here? The x-axis. There you go. Good. The x-axis is the same thing as the line y equals 0, right? Because every place on this axis, the y-coordinates are 0. And a function is positive. When we talk about a function being positive, the function means the y value, right? The value of a function is the y value. So a function is positive everywhere where it's above the x-axis, okay? So let's expand this first answer a little bit. That's just one value of x. It's one point on an entire interval of an infinite number of values where the function's positive. So where does that interval start and where does it stop if I expand this? What do you think, Mackenzie? How far could I go to the left and the right of this and still be in places where the function is positive? I could go, if the ant starts there and he's going to walk to the left, when would he cease to be in a positive part of the function? When he gets to x equals what? So he's walking down the function, still positive, right? Right. Still above the x-axis, walking down the function. Tell me when to stop. Okay, right there. Yeah, good. That's where, when he gets to x equals 1, at that spot right there, is that positive?
Yes.
It is? Right there?
No.
How come it's not? What's the value of the function there? What's the y value? 0. Okay, think about the number 0. Is the number 0 positive? Yeah, it's not positive and it's not negative, right? It's in between the two. Agreed? So I would have to stop the interval there, and what kind of endpoint would I have to use? A closed one means that I'm including that endpoint. I'm including that point. But is it positive there? It's got to be open, right? Because it's 0 there, which is not positive. So it looked like that. Now how far could I go to the right if the ant's walking down that slope? To 3. Yeah, okay, so I'm going to go. Everybody agree that that's an interval. When the ant is walking on that red interval, the whole time he's walking on a positive part of the function.
Yes.
Agreed? Good. How do we say that interval? Somebody tell me that interval as an inequality. So x is what on that interval?
0.
What about, well, x is, I want the x values now. Because remember, my original question was, I want to know an interval where the function is positive. So I'm asking about x values. Okay, so 1 and 3 are the endpoints, aren't they? So x is greater than 1. Do I include an equal to there? I don't, because I've got an open endpoint, right? X is greater than 1 and less than 3. Good. Everybody see that?
Yes.
How would I write that using interval notation? Mr. Dusso, how would I write that same thing in interval notation?
Is that the one where you just put the X in interval thing?
No, that's set notation. Interval notation only gives me, it doesn't use any variables, it just gives me the endpoints.
Yeah, so you go inside of parentheses.
Okay.
1, 3.
Good. Left endpoint, right endpoint, I've got rounded parentheses because we're not including endpoints, right?
Yes.
Make sense? Good. Okay, give me another one. Where's another place on this function where the function's positive? Okay, between 5 and 7, right? So I could also say that part right there, right? So I could say, let's use inequality. I could say where x is greater than 5 and less than 7. And I could keep going. There's another one over here, isn't there? Let's just take those two for now. This is something that the book doesn't talk about, but I just want to bring up now because you'll see this again in math later. If I want to talk about both of these intervals at the same time, what word do I have to stick in between them? What are the possibilities, maybe? Just throw out some possibilities. Okay, or is one. Or is a possibility. So the interval is x is greater than 1 and less than 3, or x is greater than 5 and less than 7. What's maybe the other one we could use? You might think would be possible, even if it's not right. And, right? I'm not going to say equal because we're talking about, it's not really an equation, right? We're talking about defining a domain here. So which one of those and why is correct? You gotta be really careful here. Think about what we imply when we say and what we imply when we say or. What do you think? It's or is the right answer. You're right. Or is the right answer. How come? Okay, it's not including both. Or means mutually exclusive, right? You can't be two things at the same time when you're talking about or. And means both have to be true. We've used and before. We used it right here, in fact. When we say this interval right here, this left interval, right? How do we say that? X is greater than 1 and less than 3, because both of those things have to be true at the same time to be on that interval, right? It's not enough to be just greater than 1. Greater than 1 could be 12, right? But 12 is not less than 3, so it's not on the interval, right? And has to be both. Okay, you can be both a, what can you be? You can be both a boy and tall, right? Does that make sense? But you can't have, for example, oh, it's a good example of an or statement. Somebody come up with one. What's an or statement? Two things that can't be true at the same time. Say it again? You can't be tall and short. There you go. Good. Good. Very good. Like it. Okay, so we could do the same thing. It'd be almost the same argument if we talked about where a function is negative. Where's it going to be negative? Yeah, below the x-axis, right? So here's an example of an interval where a function would be negative, right? Okay, and we could do the very same kind of an interval. I won't make you do it again. You already practiced that a little bit. What do we call these, though? This is kind of important. What do we call these points of transition that are neither positive nor negative? They're the points of transition between positive and negative. What's one name for those? Where a function crosses the x-axis. Yeah, x-intercept we could say, right? You've probably heard that before. There's another name you've probably heard before, and maybe you never thought about why it's called this, but what's another name for these places? So all those guys, what's another name for those? X-intercepts, what's another one? Endpoints, I mean, they could be for intervals, but just in general, whether we're talking about an interval or not, if we're talking about a function where it crosses the x-axis, have you heard this terminology? Zeros? In algebra 1, the zeros of a function, those are the places where it crosses the x-axis. Based on our discussion, why do you think they're called zeros? Yeah, because because they're on y values of 0. They're between positive and negative, right? Okay? So it talks about the y value of the function. Okay, moving on. So we got, what did we cover there? We covered positive, negative, positive values of a function, negative values of a function, zeros are in between. What about increasing versus decreasing? Give me an example of an interval where the function is increasing. What do you think?
So negative one and positive one?
From -1, okay, you're looking at the y values, aren't you? Probably. We want x values, right? We talk about an interval, we're talking about x values. So you're on the right track, but now just think of the x values. From where to where? What do you think, where it's increasing? Like 2 to 6 right there?
Yeah.
Okay, so let's look at that interval. So the ant's walking along this interval. He's gonna start there and end there, right? As he's walking from there down the function, why would that be, what's your thinking, why that's increasing? Okay, because it's above, okay. Okay. Let's add one stipulation here. We're talking about the value of the function, and whenever we're talking about whether a function is increasing or decreasing, and we're thinking of any of these ant analogies, the ant is always assumed to be walking from left to right, so he's walking in the positive x direction. So if the value of the function is increasing as the ant walks, what do you think that must mean the curve looks like there? If the value of the function, meaning the y value, is increasing, what's going on? What's it doing?
I got a little U thing.
Okay, it may be a part of the u thing, but what's the function doing if its value is increasing as the ant walks from left to right? It's going up, isn't it? Yeah, the ant's walking uphill from left to right. Does that make sense? Okay, so where is an interval then where that ant is, where the function is increasing? What's one interval where the function's increasing?
1 and 2.
Between 1 and 2, sure. Okay, if we start at 1 and we go to 2, on that whole interval right there, except one question, can I include 2?
No.
That's a tough question. The answer is no. How come?
It's
Yeah, because if I take if the function is increasing, meaning I'm walking uphill, then that implies that the next step should be higher than that step, right? Everybody agree? So for example, if we look at this step right here, there's when the ant is right there, well, his getting to that step, he walked uphill, and his next step is also uphill. So yeah, he's increasing, right? This one doesn't work though. At this spot right here, sure, the step before that took him uphill, but the next step is going to take him downhill. So the function is not increasing there, right? It's increasing prior to that. Where's the other boundary of the left boundary of the interval where the function is increasing?
would it be to like -1?
Yeah, okay, right there, good. So it's going to be at x equals 0 and y equals -1. So there's an interval where the function is increasing, right? Make sense? What's another word that we might use to describe that line segment that also would tell us that the function's increasing? What's a kind of an attribute of a line that we could use to maybe help us understand this too? If I continue that line on forever, that segment, let's just say it kept going, what are some properties of that line? Some ways you could describe it.
It's rising.
It's rising. What's the word we use for a line though when something's rising? I mean, think about how we write a line. We write a line in the form y equals mx plus b. There's really only two parts of that. And this is kind of amazing, but if you think about this, this is the equation of a line. X and y are variables, right? Those could be, x could be anything, y we're going to calculate. But these two quantities right here are numbers that are going to be properties of the line. We call those, a fancy math word is parameters. meaning their values we could dial in. What if m was equal to 2? What does that mean? What does m stand for? Slope. Yeah, and b is what?
Starting point.
Starting point or y-intercept, right? Start value or y-intercept. So by just dialing in those two numbers, I can create any line in the universe by just controlling those two numbers. By controlling the slope, there's an infinite number of values that the slope could have, an infinite number of values that the y-intercept could have, right? But that's an important one, the slope. What does the slope mean? Where you go, meaning what for a line? How do we, what's our formula for slope? Rise over run, yeah, right? It's rise over run, isn't it? So it's the steepness of the line, right? So the slope determines if it's increasing. If the slope is positive, right, that means that the function's increasing. Does that make sense? Okay. Positive slope means the ant's walking uphill. What's a negative slope mean? Going down, it's decreasing. Is this kind of, I know you talked about this, but it's been a year, right? We did geometry, we did do a lot of this stuff, and then it's been a while ago, but is it ringing a bell? Is it coming back a little bit? So that's an increasing interval. Give me an example of a decreasing interval.
The other side of it.
Other side of it, yeah. We could go from 2 down to 4, right? And that's decreasing because the slope is negative. As the ant walks from left to right, he's going downhill. Agreed? Okay. So what do we call, so here's decreasing. And I'll put another increasing one in there. You'll see why in a sec. There's another increasing one. So then what are these special points that are not included in those intervals? What could we call this point right here, for example? Because it's not decreasing and it's not increasing, but it's the boundary between the two. In calculus, in my calculus class, we spend a lot of time, probably 3 or 4 months, just finding ways to look for places like that on a function. What is that? How could you describe that? It's a transition from an increasing to a decreasing function. So a place where an ant changes from walking uphill to downhill. What is it? It looks like a peak, right? It's like a mountain peak. Starts with an M. What's the word we give that in math? I know you talked about it, but it's been a while. What is it again? Maximum. That's it. It's a maximum. So a maximum is just any place where we're transitioning from increasing to decreasing. So by the same token, now that we've said that, this one's going to be easy. What's that one? Minimum. How do I say more than one maximum at the same time? What's the plural for maximum? Maxima. Good. Maxima. So we replaced the UM with an A. What's plural for minimum? Minima. There you go. Yeah. Very good. Okay, what else are we missing? Oh, one more thing. And then we're good with this. Okay, so let's say we want to do one more thing with this. And we talked about this a little bit. In math, we like to be able to quantify things. So let's say we want to take this interval, for example, that we looked at before, where the function is increasing, and we want to talk about how much is it increasing. We want to be able to attach a number to this. Well, you already told me that this is where the slope is positive. How could I attach a number to that, though? What is the slope of that segment? How would I calculate it? Okay, be careful with the units on this because it's been stretched a little bit. But when we calculate the slope between points, don't we just do a slope triangle? Right, remember that? So we start here, and there's our rise. Now, what is our rise? Look at the units carefully because it's been distorted. It's been stretched vertically. How far did we actually move upward? 2. Okay. So, right, because we go from -1 to +1. Yeah, see how it's been, see what I mean? How far did we run? Okay, once again, the units are misleading. 2. So what's the slope of that line? 2/2, which reduces to 1. Okay, so the slope is 1. All right. Okay, we could do the same thing for, like if we were to go from here down to here, or let's just make this, we're not so messy here, let's do that one. Same kind of deal, only this time if I start here, because I always have to go left to right, don't I, when I'm calculating slope, right? Always we're moving in the positive x direction. So what's my rise going to be here? -2, because I'm going down. So my rise is -2, my run is always positive, because I'm going left to right. So what's my slope there then? Yeah, -2 over +2, which reduces to -1. Okay, good. All right, now we're going to do something weird. What if we do this instead? What if we want to start here and end there? Same deal, I'm just going to go up and over, right? Same kind of thing, I'm going to use a slope triangle again. Up to and over 10. Okay, so if I start here and I end there, my slope triangle is +2 and +10. And so the slope of the green line is 2 over 10, which reduces to what? Oops. Okay, 1/5, right? So what does that mean though? Does the ant ever, he doesn't travel that path, right? If you look at the ant's journey from left to right across this graph, really his slope is only ever +1 or -1, or he's at peaks or valleys, right? Maxima or minima. He never has a slope of 1/5, and yet that's pretty valuable. Here's an example of why that might be valuable. Let's say that you wanted to, you're gonna leave Pendleton and you're gonna travel to Portland. You're gonna travel to Portland, and you want to be able to tell your friend exactly when to meet you in Portland, okay? So when you're traveling along, as you're going by Rue Elevator, you notice that your speedometer says 75, okay? Is that going to be, potentially that's going to be useful in helping calculate when your friend should meet you there. But you traveled that same road last week and there was some construction, and it took you, Portland is how many miles, let's say 200 miles away. Say 200. We're gonna make it. Say 200, and let's say it took you 4 hours to get there. Okay, what does that tell you about your speed? Did you go 75 the whole way? No, if you went 75 the whole way, you would have gotten there quicker, right? So there must have been some construction or something going on that slowed you down. Probably more useful than your instantaneous speed at Rue Elevator was your average speed for the whole trip. How would you calculate your average speed for the whole trip? What do you think? It's 200 miles, we'll say, and it took you 4 hours to get there. What's your average speed? What do you think? Sir, what do you think your average speed is? 200 miles, 4 hours. Not sure. Okay?
60.
How would I calculate it? You just divide what? Yeah, okay, you're just going to divide 200 miles by 4 hours. 200 divided by 4 is what? 50. And the units are miles per hour, right? So your average speed was 50 miles per hour. Are you going 50 miles per hour very often during that trip, probably? No, probably almost never, right? Maybe just a couple instances you're going 50, but usually you're going faster than that, or if there's road construction, maybe you're going real slowly for a little while, right? But that's a pretty useful number to us because that's going to tell us how long it's going to take for you to get someplace and when your friend should meet you there, right? By the same token, if we want to go from this point to this point and we want to calculate how much the function is increasing on that interval, we calculate a slope of 1/5, even though there never is on the function an actual slope of 1/5. That's the average rate of change of the function. All we care about is the starting point and the ending point and the slope in between those 2 points, right? So there's a new thing. Average rate of change. All right, so there's our review. I mean, hopefully that rung a bell for you, and it's kind of coming back a little bit. Here's the next thing though I want to take a quick look at. So what we want to do now is we're gonna shift to something that's, you're gonna need calculators here in a second if we get there. We want to do some mathematical modeling. So let's look at this situation up here, and let's see how maybe this can be useful to us. So we got this. Here's the situation. We got Lyme disease is a bacterial infection transmitted by ticks. If you read through this, what it tells you is that your probability of developing Lyme disease, which is really, really bad, is very much dependent on how long that tick is on your skin. During the first 24 hours, the probability is 0%. There's almost no chance of getting Lyme disease if you get rid of the tick within 24 hours. Okay, but the next 3 days are crucial. The next 3 24-hour periods, each of those has, the probability is increasing. But day number 2, it doesn't increase very much. From 24 to 48 hours, the probability goes from 0 to 10%. That's still not bad, right? But look at day 3. From 48 to 72 hours, the probability goes from 10% to 75%. Yikes, right? And then day 4 goes from 75 almost up to 100. So you really want to get that tick off before day 3, right? Okay. This is useful to us because it gives us a way to make a prediction. So let's just say that the tick is going to be on your skin for 60 hours, right? Well, 60 hours is right there. At 60 hours, what is the approximate probability? Yeah, 40 something, right? 40, looks like, I don't know, 42, 43, something like that. Low 40s though, right? So that gives you a probability of, how likely is it that you got Lyme disease? And so if it was on you that long, probably the doctor's going to want to do something fairly drastic to try to make sure you don't get that disease, right? But if it's only been on for 30 hours, well then, it's pretty unlikely. Probably don't need to worry about it too much, right? Okay? But is there something about this that seems a little hokey? If you look at this mathematical model, it's useful, it's better than nothing. But can anybody tell me something about this that just it just seems a little contrived and probably not accurate? About the shape of that. I think that's the way biology really works. Do you think that at 47 hours, 59 minutes, and 59 seconds, the bacteria is progressing at a pretty modest rate, and then 2 seconds later, all of a sudden, it's kicked into overdrive? No. Probably not, right? What should this curve probably look like more than this? Should it have these jagged, these kind of jagged transitions? Okay, what should it do? Okay, I like the sound effects too. So it's going to do something maybe like this, right? Where it's going to go maybe more like that, where it's a smoother curve, right?
Why can't they just smooth it?
What do you think? Go ahead.
You said that 60 goes in between 48 and 72. Why don't they just space it out?
So, okay, so you could, and maybe one way to accomplish this is you could do shorter intervals. If you had more line segments, it would start to look smoother, right? There's some ways we could go about this, but one way we can accomplish this is by using some technology, right? There's actually a way that you can take a bunch of data points and you can ask your calculator for the best curve that matches those data points, and it's really easy to do. A short while ago you couldn't do this, but technology has advanced to the point where, yeah, we can do this. The process is called regression, and it's a pretty hard statistical thing. I mean, if you actually look at the formulas for how you calculate regressional curves, it's really complicated, but your calculator does it almost instantly. So let's look at an example. I don't know if we'll get through this whole thing, but we'll at least kind of set it up. So tomorrow will be short. So what about something like this? Okay, so let's say we've got a situation where a photographer is hiked through the Grand Canyon. Each day, each row corresponds to a day, right? Each data point. So each day she takes a certain number of photos, and when she goes back after the trip, she looks through and only keeps the good ones. And so this tells us on a given day how many she took and how many she actually ended up keeping, right? So what we want to do is we want to come up with a linear model. We want to come up with a line that's going to match this data. Okay. To do that, though, if we were going to graph this, we'd have to know which variable goes on which axis. Okay. So the first step we gotta deal with is here's my x-axis. Here's my y-axis. The x variable is the input variable. The y variable is the output variable. We know that. But between these two, we got to decide which is which. Well, there's one correlation here that kind of helps. The input variable, or the x variable, is also the independent variable, right? The output variable has to be the dependent variable. What's the difference? Dependent versus independent variables. What do they mean? We'll say it again. It's true, the domain would go with the x values, the input values, the independent variables. But what's the difference between, think about the meanings of the terms independent and dependent. Say it again. Okay, so independent is going to be the one that stands by itself, and the dependent variable is going to be the one that we're going to calculate based on the independent variable, right? It depends on the independent variable. So which one of these would be independent and which would be the dependent quantity? What do you think? Think about the two things that we're looking at here. The number of photos taken and how many of those are actually kept. We want to be able to set up a situation where we can predict maybe one of these quantities based on the other. Yeah, okay, good. The independent would be the photos taken. She just takes a bunch of pictures each day, but then based on the number that she takes, maybe that's going to help determine how many she actually keeps, right? Okay, so independent, dependent, right? When we graph those, then what are we going to get? So we got taken on this axis, I'll abbreviate, and kept. And so maybe we're going to end up getting some kind of a linear relationship when we graph those, hopefully. If we do, then that's going to create a mathematical model that we can use to make predictions. Okay, but how are we going to come up with the best fit line? What are some characteristics of that best fit line? What do you think? What are some things that if I want to find a line that's going to sort of be the best fit line through that distribution? I know you've done this in Algebra 1. How do I draw the line? What are some things that have to be true? Is this a good line right here? No. How come?
Through all the points.
Oh, it's got to go through the points. So I got when you say through the points, you're saying that half the points should probably be what? Half above, half below, maybe, right? That makes sense? Okay, so then based on that, is this a good line? It seems like I got half below and half above. But what else does it have to do? Something else. Well, a lot of times it goes through the origin. But what else, though? There's something that doesn't always.
The direction.
Okay, so it's got to follow it's got to be as close as possible to all the points at the same time. So we want to go the general direction that the points are traveling in, right? So that's not a good one, but would you agree that something like that might be not so bad?
Yes.
Right? Okay, so if we do this though manually, if I gave you all a copy of this and you all put best fit lines on there, you might do a great job, but are any of them probably going to be exactly the same? No, probably not, right? Probably not. And it's going to be difficult for us to get exact equations for those lines. Wouldn't it be great if there was a way we could all agree on the best fit line?
Yes.
And it would be correct. There is. Here's how you do it. I'll show this to you quickly today, and then tomorrow maybe we'll go through more steps. But this is what you do. So if you have a graphing calculator, get one if you want to, or if you've got one, break it out. Here's mine. Okay, all I'm going to show you today is how to do a scatter plot, and that'll be enough. That'll be tough even to maybe get through that.
I have 3 batteries.
Okay, real quick, here we go. See if you can follow this, and we'll spend a little more time on it tomorrow. So to do this kind of thing, we want to go to, this is a statistical process. So this is like, we're going to utilize statistics to come up with the best fit line. So we're going to push the stat button, which takes us to the statistics screen. Okay, real quick, the statistics screen is broken up into 3 menus: the edit menu, the calculate menu, and the test menu. We'll never use the test menu, but we'll use the other 2 quite a bit. So when we want to input some data like this, we're going to go to the edit screen, and we're going to choose edit, which is number 1. So I can just hit enter. So now look what you see. Now you see.
Wait. How'd you get there?
Okay, so I went stat, enter, either stat 1 or stat enter. Okay, and that takes us here. If there's data in there, which there might be, if there's data in there, we want to clear that out because we want to put our data in there. So to clear it out, you go to the top of the column. So I'll go up like to L1, which means list 1, and I'm going to hit clear, enter. Okay. If you accidentally hit delete instead of clear, look what it does. I can't, now that L1 is gone, and you have to buy a new calculator. Because the L1 is, no, you don't have to buy a new calculator. You can get it back. Sorry. You just go to stat 5 for setup editor and hit enter. And now you get, if I go back to stat, enter, there it is. I got it back. Okay. So you want to hit clear though, not delete. So now we'll go over and we'll clear L2. Clear, enter. And now we're just going to enter all this data. Now, notice that we said that the photo is taken. That was going to be our X variable, right?
Yes.
That's X and that's Y. The X variable or the input variable always has to go in L1 and Y goes in L2. So now we just input this stuff. So we can be quick about this. We get 1, 1, maybe. We get 1, 1, 7. And if you hit enter, it just pops it down. That's the easiest way to do it. What's that? So all I'm doing now is I'm just putting those numbers into L1.
Wait, I just like that. I don't know how to get this. Okay, so I'm here. How do you? It's not.
Is he not doing it? Come up and show me real quick. Oh, listen, please.
There is a meeting in the Commons for any student interested in manual labor over the weekend for Roundup. Any student interested in manual labor over the Roundup weekend, please go to the Commons. That's where you
Oh, you're good. So you just put numbers in. So we can just go 1, 1, 7. Oops, you already, I messed you up.
over the weekend for Roundup. That's where you follow the Commons. Thank you, and go Buckaroos.
There it is.
How'd you do that?
That's just kind of stuff.
Oh my goodness.
Okay, real quick, we got to go here, but look at this. Here's what happens. Shh, look up here real quick. So now I got all that data in there, right?
Yeah.
If I want to graph it, there's a shortcut. If I just hit graph, it's really unlikely that I'm going to actually see what I want to see. So what I have to do is this. I have to go to y equals. Oh, there's a lot of stuff on there from last period. Okay, so if I go to y equals, I'm going to turn everything off or delete. I'll just clear those equations for now. I don't need them anymore. Okay, but I'm going to turn on plot number 1, right? And all I do to turn on plot 1 is I go up and highlight it and hit enter. If I turn on plot 1, now if I just hit graph, I don't really see any of my data. But if I want to see the data, I can go to the zoom menu and just hit zoom stat. So zoom 9 is going to fix the window so my data shows up, and there it is. There's my scatter plot. Okay, that's giving me, now tomorrow we'll look at how we can take that scatter plot and come up with the best fit line. So turn in your calculators.